now what we're going to work on is working on significant figures and adding and subtracting. Subtracting. All right, so check this out. There's two math rules that we're going to talk about. First math rule is measured data must be of the same kind of dimension and have the same units before you can add and subtract them. For example, you cannot add 5 seconds plus 3 meters. That doesn't make any sense. That doesn't give you 8 meter seconds. It just means you have 5 seconds and you have 3 meters and you have those two as separate. You can't add those two together or subtract them for that matter. And obviously the seconds and meters are completely different units, but sometimes people think, okay, well, what if I add 5 meters squared plus 3 meters? Well, you can't do that either. That's adding an area to a length. It doesn't really make any sense at all. So the second rule is the sum or differences. Man, I'm really having trouble with the word subtraction. All right, sum or differences of measured data cannot have greater precision than the least precise quantity in that sum or difference. All right, I'll show you what it means through this example problem. It's pretty straightforward. I just want to add 1.008 grams and 16.00 grams. Now the question, so both of these have 4 significant figures. See, there's a significant figure here and a significant figure here, and then these two guys in the middle, even though they're zeros, they are completely significant because they are trapped in between these two significant figures. And then over here, these first two are obviously significant, but then these two at the very end are also significant because those are trailing zeros at the end. But the thing is, which scale did I use that was a better scale? It may have been a more expensive scale or a more accurate scale because it gave me more numbers, and I assumed that I recorded the right number sig figs down when I took the measurements. And the answer is this one over here must have been a more accurate scale because it gave me more places after the decimal point. Over here I have 3 places after the decimal point, and that's how precise I got. I can measure this thing up to 1.008 and state with confidence that that's how much, how precise I want my measurement to be. Whereas this other one, I might have used, I don't know, a bathroom scale. Actually, your bathroom scale wouldn't be able to measure 16.00 grams and really be able to state that with accuracy, but maybe I use some other cheaper version of the scale. So what I mean here is when you add these, you want to add these kind of old school way where you align the decimal points. I think we taught that to you back in grade school. So I'm going to add 1.008 plus 16.00. And then you add these straight up and down. 8, 0, 0, 7, 1. And you drop that decimal place down. All right, nothing new there. This is just old school adding. But here's the thing, the least accurate measurement in this summation, in this problem, is actually the 16. And it only goes up to the hundredths place, 2 places after the decimal. So you have to cut off your answer to only go up to the hundredths place. So you just go 17.01 grams. And then sometimes what you'll see is maybe you'll see it like this with the squiggly equal signs. That just means I'm not approximating it, but what I'm doing is I'm kind of rounding it off to make sure that I have the same number of, or not the same number, but the correct amount of significant figures. And this squiggly line means approximately equal to, as opposed to writing every single number down on your calculator that you have. And that's the problem that we're having here is we have students and chemists and whatever calculating things out and then writing every single number down when obviously they didn't measure things to that kind of precision. And the problem is they're reporting numbers that are with much greater accuracy than they should be.